Now the first thing that I will show is ridge regression. For that you will need again a package which you do not need to install. It is always installed by default. You load it, MASS, and the function that you use is lm.ridge, pretty much the same syntax as lm, only here you have to specify lambda. You can specify a value of lambda, which is the lambda of the ad hoc formulation, or you might specify a list of lambda values as we have done here if you still do not know what value of lambda is the best thing. Here I have done that thing. I am using a sequence from 0 to 2 and the sequence is of length 200. So a list of values of lambda 0 and then 0 plus delta, 2 delta, 3 delta, where delta is 2 divided by 200. And let's do that. I will do it. Now the output, if you try to look at it, will be something big. It has got all the estimated coefficients and all the different values of lambda. And it is not very desirable that you look at fit by simply typing fit and hitting enter, because all the things are sort of garbled. So you want to find out the coefficient using the coef function. I will take that. I do not care about the intercept term here, so I will keep that out. And here are the lambda values that I am using. So I will plot the different fitted things, that is beta I hat lambdas against lambda. So I will get 3 different curves because there are 3 different coefficients. I am not considering intercept term in the plot. And I am using the function matplot, which is a function in R. So I will do the plot. And here is the plot. Now, it is somewhat difficult to understand which line corresponds to which, but I will tell you that the black line, you see the black line, it just sheet goes up and then becomes flat. That black line is the coefficient of x1. And here I am showing lambda. The red dashed line is the coefficient of x2. And the green line, that is coefficient of x3. Observe that the coefficient of x3 remains essentially flat. And coefficient of x1 and x2, they just change drastically. So initially one of them is less than minus 15, the other is more than 5. The moment you increase lambda a little bit, they come down, and after that they become stable. So when you are taking lambda equal to 0, you are actually doing just ordinary least squares. The moment you are going into real reach, that is increasing lambda, making lambda strictly positive, the things are becoming stable. Now the coefficient that is not locked in a multicollinear relationship, that is always flat. The green line is always stable. But the other two things change a lot. This is one thing that indicates that multicollinearity is present, and that the first two coefficients, or the columns of the first two columns of the design matrix, are involved in a multicollinear relationship. So this plot, which is called the ridge trace, is also a diagnostic tool. Naturally, you will choose your lambda somewhere slightly more than 0, that is where these things are stabilizing, and these stable values are what you will use with more confidence than the original least square estimates, which are less than minus 15 and more than 5, etc. Now, how do you really do this choice of this? So, you can take a look at the coefficients. So these are all the coefficients, as I say, not very appetizing. It shows you all the different values of lambda and the various estimated stuff. So huge thing. I have asked for 200 different values of lambda, and the first column gives you lambda, the second column gives you the intercept, and these are the coefficients of the other thing. So you basically looked at a plot of these things. Now, how do you choose the value of lambda? Well, the best way remains that you choose it by looking at the ridge trace, because that gives you a subjective understanding. But in case you want an objective way of choosing it, not that people care much about that objectivity here, there is a function called select. You just say select fit, and there are certain ways of estimating the tuning parameter. HKB is one method. I really do not know what is the exact way that they are doing it. And they are giving you this value. The best lambda hat is this. It's pretty small. You see, even with that pretty small lambda, you are getting a lot of improvement. There is another one which is called LW estimator, which is also pretty small. And GCV is generalized cross-validation. That is basically the idea that I mentioned earlier. You do cross-validation, you split it up into two parts, training part and test part, etc. And that gives you this value. Now, you see the values are quite different, but that doesn't matter because you saw that the moment lambda is slightly more than 0, the things are essentially stable. So the choice of lambda is not that crucial. So that is why just looking at ridge trace is usually enough instead of using these blind algorithms. So these are not that popular algorithms. Cross-validation is a popular algorithm, but this HKB and LW, they are not. So that is ridge regression.